So this is just going to be a very high-level overview of how, in general, you can think about zkVMs and how to view how they work generally, like to have a rough mental model of how they operate. Yeah, so hopefully I plan for around 30 minutes of discussion, so let's hope we cap off around yeah, 4 maybe. So zkVMs. What do we think when we say zkVMs? Does anyone has an answer for this? Like, what do you first think of when you think of zkVMs, or when you hear like SP1 or?
A virtual machine with ability to generate a proof.
Yeah, correct. Yeah, but even before that, maybe what is a VM, right? Like if we take away zk, what is a VM?
Probably an abstraction model of the physical machine.
Right. So in a sense, you can think of it as a program that runs another program, right? Because you have, let's say, Java virtual machine, right? And it runs Java programs. But to run those Java programs, you need to write the program that runs those programs. So same for EVM, right? Like if you have an EVM, you have like a program that runs EVM smart contracts. That's it. So in that sense, I think it's right to think of zkVMs as something that sort of, people often say that it takes in a program and then produces a proof of the execution of the program. But actually, it's more of like it produces a proof of the correct execution of the machine, in that sense. So you can implement the zkVM wrongly, and it can still produce a proof of saying that the program was executed correctly, right? So it's a slight nuance, I guess, and then that's sort of where a bit of differentiation needs to be taken care of, I think, when you think about zkVMs. There's also some like discussion on how people are saying that zkVM is a bit of a misnomer because it actually isn't zk, right? Because it doesn't really provide privacy. So some people are saying like to call it a succinct, I'm not sure, but succinct verifiable VM or something, like SVVM, let's say. Because it produces a succinct proof and it's a verifiable execution of a program, let's say. So, yeah. So, yeah, so with that in mind, let's go on to how an actual zkVM works. So, how I picture it, I see it as there being 4 phases, and we'll talk about each of those 4 phases in detail, or in rough detail, I guess, like touch a bit here and there. So there is execution, and then there's trace generation, which feeds itself into the proof system. And that produces a proof. Let's say pi. Right. So this is actually sort of the order of things I'm going to talk about. Basically, you have a program that gets executed and some trace is produced. And the trace is fed into a proof system which outputs a proof. Right. So let's talk about execution, I guess. So in execution, there's actually nothing zk or cryptographic about this stage actually. And I think a good way to think about the execution stage is actually just that it repeatedly executes the fetch, decode, execute cycles, like how a CPU would do. So you have a fetch, so the VM fetches some instructions within the program that is compiled to whatever it supports, and then it decodes those instructions and executes them. So this can be, for example, I'll just write some RISC-V instructions, for example. So for example, let's say you have an add instruction, which is something like this. Let's say somewhere in the program you have like an add instruction, which is like you add to a destination register from two target registers, let's say RS1 and RS2. So you're doing plus here, RS1 plus RS2, and feeding it into the destination register. So then the fetch would fetch an instruction like this, decode it to mean this actual instruction and actually execute it, right? And then you just have a list of these instructions all the way until the last instruction, whatever it is. Just like, let's say there's a halt instruction. So there's actually nothing zk about this. So this is just purely, let's say if you want to implement a VM, this is how you do it as well. Until this point. So this point where you execute the instruction, and remember when I said earlier that you're proving and verifying the correct execution of the machine, which means that for this part of the program, or the VM rather, you need to show that it's executed correctly, basically, right? So the VM can just do this, like plainly, right? But how does a zkVM know that you did actually add these two registers and stored it here, right? So this is the part you have to prove. And this is also the part where I guess discussing some of RISC-V's advantages is relevant, I guess, because RISC-V's instruction set is relatively small. So at least it appears like RISC-V, for example, if you support the 32-bit register, 32-bit instruction set called RV32I, it's about, let's say, 50 instructions. So by that I mean like different types of instructions. So let's say this is one instruction, right? And then for ARM, for example, if you want a similar implementation, this would be about 500 instructions, I think. So if you go back to what I say about having to prove the execution of the instructions, that means for every instruction, you need to be able to prove them, which means you can think of like the work needed to prove 500 ARM instructions, right? So it's part of the reason why RISC-V is sort of preferred today, I guess, because of the small instruction set. And also it's quite flexible because you can take and add in instructions if needed, depending on what you want to implement. Yeah.
Can you give us an example to illustrate why ARM needs so many kind of instructions?
I actually don't know. So this is actually somewhere I heard I heard on the podcast actually. So the Jodes, the people who worked on Jodes, they looked into this and then they mentioned that to get the equivalent instructions supported, you need around 500 instructions. And I'm guessing they, yeah.
I think for RISC-0, they have like a component of structures. So in ARM, they just have like tiny instructions inside. So maybe like add and multiply. The RISC-0 will have more instruction. One instruction contains more things inside. That's why.
It's also a reason that a lot of instructions are not. This file doesn't give you a lot of instruction. It says, okay, if you want to do this, we will have like 2 or 3 instructions do the same thing, so we don't need to really provide you all these instructions.
Yeah, yeah.
So if you check, so there is something called pseudocode. When you type pseudocode, the compiler, the assembly compiler will convert your pseudocode into real code. It will increase the number of instructions, but it will reduce the size of the instructions.
Yeah. Okay, let's try this. Okay, yeah, this is better. Okay, yeah. There's also some like non-technical reasons, I guess, or slightly technical, that RISC-V is open source standard. Then a lot of, and it also compiles from a lot of languages compiles down to RISC-V instructions, like Rust, for example, which everyone loves, or C as well, and so on. Yeah, there's also some other issues at this stage, but so there's the issue of trying to produce a reproducible build, for example. But so just I don't want to go too deep into this, but just on a high level, we had to kind of deal with this a bit. So each person's computer has different versions of, say, like GCC or LLVM, let's say. And then when you compile a program, you could have different results, right? And that could affect how you prove and verify the program memory. Because the layout might be different, you know, a 32-bit computer might compile differently from a 64-bit computer, for example. Yeah, so this is kind of what I want to say for execution. Are there any questions or comments?
Could you highlight what again? What you mentioned reproducibility again?
So like,
What was the significance of that?
yeah, so so when you compile a program, right? Let's say you have a source, like a Rust source code, right? Like a Rust, like a program or whatever. Depending on your compiler version, it could have different. The binary might be different. So if you compile it using Rust C 1.81 versus the nightly version, let's say, it could end up being a difference.
So does it tie back into what we use with Slack, or how is this, what is this pattern?
So this ties back into this just this stage in general.
Oh.
So it applies to any ISA that you want to compile down to.
So reproducible build, it's good because it always compiles out to the same trace, and that's what we want. Is zkVM, is that what you're trying to say?
Yeah, because otherwise, if I manage to prove and verify the execution of a program, someone else might not be able to do the same.
Okay. So this is what you want to achieve in zkVM.
Yeah.
Oh, got it. Thank you.
Yeah.
Thank you.
Yeah. So while I erase this, and we'll talk about trace generation next, but I'll talk a bit about reproducible builds. So there's some projects, like, I'm not sure, there's a bit of obscure projects, but it's called Nix. I'm not sure if anyone uses Nix, but they're also trying to solve the issue of reproducible builds. And some teams, like for example, if you tried out RISC-Zero's examples, I believe in their program, or in the program to build the programs, they use Docker to guarantee reproducibility.
You mean
Right.
the compiler or the compiler of the compiler?
Sorry?
You mean the compiler or the compiler of the compiler?
The compiler of the guest programs.
Okay.
Right.
So they fix the environment, they ensure that everything's the same by using Docker. Okay.
Yeah.
So that's how they ensure reproducible build. Is that what you're saying?
Yeah.
Oh, got it. Thank you.
So, but that's still like, yeah, that's more of like a
Hack.
engineering question, I guess, rather than a ZK question.
Okay.
Because yeah, there's some other teams doing that research as well. Okay, so let's talk a bit about trace generation. So now that we know that you're doing this fetch, decode, execute cycle, what do we do with that information, right? So the simplest way to consume that stream of data, right, is to store it somewhere. But I guess before we talk about storing somewhere, we kind of have to talk about what's the link between trace generation and the proof system, right? So depending on the proof system that we're using, we have to generate the trace in some manner that the proof system is able to prove later on. So for example, if you're using stars, for example, then you would have to lay your trace out in like air, let's say. Then you can prove it, right? Or let's say like you want to use a plot or like RCS, and then it depends on like how you want to. So this decision sort of impacts this stage, right? In some sense. So I'm gonna talk about things from the point of view of air because that's where I know best, I guess. So I'm not too sure about the other ways of doing things.
Okay.
So in order to get a proof out of the proof system, you need to generate a trace that conforms to the proof system. And in air, what we have is a uniform table, right? So according to what we had just now, we talked about CPUs and how it executes the fetch, decode, execute cycles. And we need to store that information somewhere. So we can have a CPU table, let's say, and this would store our trace that's going to be generated. So we can have a CPU table. It's a very simple example of a table, you can say. And what we need here is the data that will be required to prove our constraints later. So very simply, just on the VM level, right, you would have a clock, let's say, and the type of opcode that it's running, right? So like in the previous example, so let's say your program starts at some clock 0, and then you have an add instruction, let's say. And of course you would have other information as well, such as like the register, right? So you have, let's say, destination register RS1, RS2. And let's say you add the values in register 5 and 7 into register 2, let's say. So this would be one table of the CPU. And then let's say we have a second instruction, which is just, say we have like an add I, which is, so don't worry about the opcodes, it's just different instructions in the RISC-V architecture. So, and then clock 2, let's say we have like a store bytes.
it's okay.
So we could have a structure like this, right? But this would get really big if, let's say, we have, if we want to support every opcode, right? And let's say we have like a mall, or even like if we have like a jump instruction, right? Which is, let's say, a branch instruction. So B and E, let's say, which is like branch not equals. So you can imagine like if you have an if else statement. So you could have a lot of different instructions, and then you could also constrain them in the same trace table. Remember that each value here is something that we want to constrain later on, in some sense. So one example would be, let's say, your clock, right? What's a constraint here that we can think of that where we might want to enforce?
Plus one.
Yeah, right. Plus one, right? We need to make sure that it's always ticking up. So like clock prime equals to clock plus one, right? So this would be what in R would be called like a transition constraint. And then we also need something like boundary constraint, let's say. And in this case, it's a very simple example that clock must start at 0, right? And this would be a boundary constraint. Boundary constraint and transition constraint. So we'll talk more about these constraints later. Some detail, but basically we're laying out the table in a sense that we can enforce these constraints. And if we think about the number of opcodes that we have to support, like add, store bytes, blah blah blah, you can imagine that the table is going to blow up, right? We're going to get a lot more things, let's say. And even, let's say, registers, right? So RV32I supports 32 registers. So let's say we implement it very naively and have 32 registers. So we're gonna have like, so this should be, I guess this should be 0. Or rather, okay, no, this should be correct. But then we have like reg 0 all the way to, say, reg 31. So you can imagine that we would blow up this table in size, right? And this would become very difficult to prove. Because the bigger it is, then the more constraints this one table would have to evaluate. So what can we do with this big table? Right? Yeah. Encode it?
Split it.
Okay.
Split it copy constraint.
What was it?
Can you put it in a small table? Split them up.
Wow, that's an excellent answer.
Wow, guys.
Right, correct.
Split copy constraint.
So, yeah, correct. So, let's think of one example where we can do that, right? So, for example, range check is the most popular example, I guess. So, for example, during the execution of a program, there are certain values that we want to keep within a range, let's say. So, let's say very simply, right? If we add two numbers, we want to make sure that this value doesn't fall out of range of the field, let's say. Or rather, doesn't fall out of
The bits.
what the VM supports, right? Because the field can be larger than
The bits.
yeah. So, for example, if you're using COM2, for example, you'd be using the Goldilocks field, which is like a 64 bits, which is represented by a 64-bit number. But if you're building a 32-bit VM, then you have to like range check within 32 bits.
Okay.
So you can do that here, right? So let's say the most common, the very simple way to range check is just to do a binary decomposition, right? And then let's say check that they still fall within the set of zeros and ones when you do a decomposition. But what you can do is also do a lookup, right? You split it into a smaller table and then do a lookup that way. So if going by this original construction, right, you can do a lookup here. So let's say you want to range check, a very simple example. Let's say you want to range check 8 bits. So you do range check U8, let's say. So you want to check that things fall within U8. And what we can do is use something called a permutation argument, which basically means that you're checking, let's say this number 2 falls within the range of 0 to 8 bits, so it's 255, right? So what I was talking about earlier, what you can do is you can do a bit decomposition of, like, let's say, then plus x1 times 2 to the 1, and then so on, right? Until xk minus 1 to the power of k plus 1. So this is like a k-bit decomposition. So you can encode this within the table and then check it that way, but that would be too expensive, right? Because if you have to do this for every value in the table, I can imagine that would be very expensive. So before we get to the small table thing, what we can do is actually, because we know that the values fall within this range, we can put all the values that we know in this range somewhere else, and then do a lookup to that column, let's say. So what we can do is put this here, right? And we put all the possible values in this range in that column. So we can do like 1, 0, all the way to 254 and 255, let's say. Yeah. But the common thing to do here is to do what Jen suggested and say, split this into a smaller table. And the reason for that is actually because R sort of requires your table to be uniform in shape. So if one column is longer than the other columns, you have to extend the columns. So let's say something is longer than 255, which is most probably going to happen. You're going to have to pad this with 255s all the way until, let's say there's like 10,000 more rows. So you actually don't need to do this, and you can take this set range of values and put them into another table, a smaller table, let's say. So this is the CPU table, right? Let's say we have a special range check table. And we just call the column value, let's say. And we store all the possible values of the U8 range here. And then what we do here is permutation argument or lookup. So given this, let's say we want to range check this register. Like We want to make sure that all the results are within a certain range. So let's say that's like 1010, blah blah blah.
But the DSD is like this, the destination memory register, right? Or like the actual value? Or we're making it simple for this case.
This would be the result of the
Result? Okay.
sorry. This would be the register. Sorry, you're right. Yeah, correct. So this would be the result, the register.
Okay.
So we can use a different example, maybe. Let's say we have a 8-bit address space, right? It's a very small address space, but let's use it. So we're storing and reading from an 8-bit address space. So maybe we write into address 0, let's see, 1050, let's see. And the lookup we want to do is basically check this column with this column.
Okay.
But this is a very lengthy example. So typically you would probably have like a 32-bit address space, and then you range check that against a 32-bit range check. But then what people do nowadays is like they split the 32-bit range check into two 16-bit limbs, because otherwise, if you do like a 32-bit range check, that table would be very big. So 16-bit would be something like 65K rows of the table.
Sorry, what does the address stand for?
Oh, so like it's for memory.
Oh, okay, I see.
So if you read and write from a memory address space, and here we're assuming a very small address space, which is just an 8-bit address space.
Okay.
Just so I can illustrate the example of an 8-bit range check. Okay, let's see. So this is also kind of the idea between of what you see in SP1, for example. People like they're saying like, hey, we have precompiles where you can easily add and remove quote-unquote chips, but they're really just tables like this. And I guess I'll erase this as I explain this. But this is about it for the trace part. Yeah.
Just a quick question. So I understand the idea that instead of like, we have another table where we can just do the lookup.
Yeah.
In your previous example, we had another column inside the other table where we had, because where we had all the possible values that are in the range.
Yeah.
And the reason we move it out so we don't have to store within each row. Is that it?
Yeah.
Okay, okay.
Yeah. Because otherwise you'd have to pad.
Yeah, it makes sense.
Yeah. So yeah. So I'm going to speak a bit more about this while I erase. So, but that's it for the trace generation part. If you look into the code of say SP1, generally you can think of this zkVMs as having tables and lookups, these two components. But they have different names for them. So in SP1 they call them interactions. Like one chip interacts with another chip.
Interaction is the lookup or?
Yeah.
Okay.
And then in, let's say, Plonky2's zkEVM, they call it the looking and looked table. So one table looks into another table.
Okay. But they're all lookups and behind the scene.
Yeah, pretty much.
Okay. Thank you.
So you can think of them as just lookup tables and lookups, basically. Okay. Okay, so we're done with this part. So I guess there's a few things to talk about here, and let me draw part of the CPU table here again. So let's say we have this. So eventually, all the columns in the table will become polynomials, and you evaluate these polynomials to be 0 at some random challenge point. And that's sort of how you enforce those constraints. But to enforce those constraints, you kind of have to write the constraints, right? And you can think of this CPU table also as like a sub-circuit. Like the whole zkVM is a circuit basically, right? And the CPU table is a sub-circuit. Then you would write things like, let's say, so in air, you have like the transition constraints and the boundary constraints, right? And then in funky trees, let's say API, you can do something like next clock equals to clock plus 1. So this would be like a constraint. And let's say you have an add instruction, right? Depending on how you implement it, what you can say is that you, let's say you do like a lookup. Maybe it might look something like in this in this evaluation function, you can say like, hey, I want to range check the address column, let's say. And this would sort of happen for every row in the trace, depending on how you implement it. But you have to write these constraints out for each table. And I guess this is also where you see like the common quotient check, right? Like this check where you have quotient and then a constraint polynomial multiplied by some vanishing polynomial, right? And if this equality holds, then your constraints are satisfied. So for every table that you have, you write the constraints, and all of them go undergo this check. It's a quotient check. But there's something we haven't really addressed, which is the range check, right? How do we, if we're doing this check, how do we actually do like this? Because this requires two tables, right? So in this case, one table, or rather both tables, would have to quote unquote call this range check function, let's say. And one would be the receiving side, and one would be the side that sends the lookup in that case. And I guess this is where we can talk a bit about logger, which is what's quite a few teams are using right now. So maybe you can talk a bit about that. So logger basically says that if we have two relations of, let's say, if you have two columns of A and B, we can enforce their relationship in something like this. So you can think of this as the looking table And you can think of this as the looped table. So, and this is the multiplicity, which is the
How
number
many
of
times?
times something happened or some value occurred in this vector.
A.
So
Okay.
yeah.
Okay. Got it.
And then you might think that, hey, where did this alpha come from, right? Like what is this? So that's actually part of the Fiat-Shamir heuristic.
Oh,
that we're
actually.
doing.
Okay.
So after you've generated a trace, you have to commit to the data within the trace. And a lot of zkVMs now, they work with this sponge construction, right? Where you absorb and then I think you squeeze to get output. So along the way, when you generate the traces, the hash function absorbs the data that you've collected along the way. Some literature call it the transcript, right? You have the transcript of the execution trace. So you squeeze, you absorb whatever has been committed so far, and you squeeze to get an extension field element. So this would be something that you get from here.
Okay.
It's called FS. So if you Fiat-Shamir to get this.
Okay.
I have a question. So does the squeezing process happen also in the verifier side?
Yeah, both sides will have to do the same thing.
And how many times will they squeeze? It depends on the length of this trace.
Depends on how. Depends on what you need to track.
Absorb. How many times does it need to absorb?
So it depends on what you need to track, because that depends on what your transcript is. Because in the case of a zkVM execution, the transcript means the entire execution of the program, right?
So does the verifier also runs absorb?
Yeah. You can think of it as like a agreed upon algorithm, right? That's both sides are agreeing that, hey, this is how we're gonna get randomness in our proving and verification.
But then the runtime of verifier could be linear to the trace length.
Sorry.
But what about the time of the verifier? So if it calls the absorb like length times. So yeah.
Okay, sorry. Let me finish. I'll let you finish.
Yeah. Suppose there are n rows in the trace. So shall the verifier call the absorb like n times?
Yeah. Basically, yeah.
Oh, I think I can. Let me try to rephrase. Yeah. So that doesn't mean that the verifier also has access to the trace, because to generate like the randomness via Fiat-Shamir, the prover and verifier needs to give the hash function the same inputs per se, right?
Yeah.
So that means if we naively use the trace, that means the verifier will also naively read the line 111, and that will incur the linear time. I think this is right.
But then it won't be a succinct.
Exactly. So I am wondering if the transcript is somehow hash and committed, and then we use that.
So they would receive the commitments to the trace.
I think the commitment is still here.
And then what the prover absorbs is the commitment as well.
And then the verifier need to be convinced that the commitment is bound by the full trace.
Yeah. And so to answer your question of how many times they need to absorb,
So constant time.
oh, you're talking about in terms of complexity, or like, or yeah. Yeah, it depends on how long your trace is.
I guess this one also differs from zkVMs to zkVMs. I don't know.
Possibly.
Okay.
Possibly. But generally, your challenge needs to attest to the execution of the entire program, right? The entire like process. Because if it doesn't, let's say your program runs for this amount of time, right? Let's say this is the end, and your like if your challenger doesn't, like if your hash function doesn't absorb at this point, let's say, how could you know that something didn't?
Yeah, no,
Yeah.
incorrect.
So yeah, you squeeze like you absorb along the way like this, and then all the way until the end. Let's see. So okay, I'm taking a bit too much time, but yeah, but I guess that's the end of the proof system part as well. If there's any questions.
And so how to guarantee that the trace is valid by the binary of the execution?
By the what, sorry?
The binary, like the RISC-V ELF, how to make sure that the trace is connected with the ELF?
Make sure that the trace is connected with the ELF.
Yeah.
Oh, so you can use a hash. That's linked to what we mentioned about reproducible builds. Because if you hash the ELF, and if it isn't reproducible, then you don't know whether the trace is linked to the ELF, right?
Will that be like a read-only memory check in the proof system?
Yeah, it should be part of your constraints. Like if you're saying like if the ELF has some read-only memory, right? And then yeah, so that should be part of the constraints.
Okay, so the constraints contains CPUs and the fetch operation and the memory check.
So you can have something like a memory table. Let's see. And then depending on your implementation, in that case, at the initialization, right, you would have loaded all the memory inside the ELF. Let's say.
What? I don't understand. What's it talking?
The memory. So he's asking if how do you check the memory of like an ELF, like a read-only memory?
What do you mean read-only memory?
So like whatever. Let's say you have like global variables of ELF, right? Like const variables. Are you talking about that? Are you talking about something different?
Sorry? So what I'm asking is, suppose you have a static binary file, like ELF,
Yes.
and how to guarantee that the trace is the execution of that ELF instead of some program else?
I think there's a process procedure that gives you that. So when you load the programs, there's a part of generating trace which is loading your program.
Yeah, so the bootload, should the bootload process also be part of the constraint system?
Yes.
So
I think there is this part. Constraint that you need load the correct ELF.
So what's the usual implementation for this? Will that be a read-only memory or other technique?
I don't know, but you can check if there's a called process trace generation. There's part of the program.
Okay, just yeah. Yeah. So maybe Wang Yang is right about this. That you do have to constrain the bootloader, but at that point of time, I think what we were thinking is just using the program hash, let's say, right? Because then you can ensure that in that way, whatever you've loaded is whatever is getting proven.
I think there's a setup stage where you will need the program to generate a program the hierarchy. And after that, you will, then probably in that step, you already load the program into the. So when you start execution, the program key and the hierarchy fixed in your VMs.
Do you mean the verify key contains the?
I don't know exactly what that can contain, but what I mean is that thing is generated after you load the program.
We can maybe talk more about this later, about the memory, because I'll be interested as well. We can discuss more on that. But so yeah, we've covered the proof system, and this part is probably going to be a very short part. So when you get the proof out, what people are doing now is they're wrapping all the sub proofs into a smaller snark proof, let's say. So most teams are thinking of, like, let's say you have like a VM, right? And it's producing a lot of proofs. So, I mean, this is pretty much, I think, what SP1 and RISC-0 is all doing. So they're like recursively proving proofs and wrapping it up in a final proof, which is usually 1216, or it can be like a F-log as well, I guess. And then you get like a small proof. It's called pi. Okay.
So does like pi 1 and pi 2 part of the trace or different?
Oh, right, yeah. So what we talked about earlier, they produce one proof, let's say. One proof of the entire execution of the VM. But in this case, this would be the trace being broken up. So this would be like one big trace. And in this case, this would be, say here. And then this would produce pi 1. And this would produce pi 2.
So how do you prove the continuity of between pi 1 and pi 2?
So you would need some constraints to prove and check the start and end position of each section.
So due to recursion, this total constraint will be checked?
Yeah. They're somewhat separate, because during recursion you have like a recursion circuit, but then this is the splitting up is more not really for recursion, but it's more for parallelization. Yeah. So here you can prove them in parallel, and then this one is the recursion part, right? This section. So this splitting up of the trace is done purely for performance reasons. And then this is what the recursion circuit does.
I think memory too, right? Because I think for the VM, of course, you can have like up to billions of rows.
Yeah.
From what I remember, they also split up the trace because you just can't prove a billion rows at the same time.
Exactly. Yeah. So, yeah, for memory reasons, that's a good point. In some workloads, for example, if you prove an Ethereum block, you would necessarily have to split up the workload into different traces, into smaller traces. and then prove those traces separately. This is especially true if you want it to run on a powerful consumer laptop. Let's say. Yeah. Yeah, I think this is what I wanted to say for the last part, because they all produce they pretty much all produce log proofs, and then wrap it in a smaller proof to put on chain. Let's say, or most zkVMs right now, I guess.
So should the public input of each pi1, pi2 to pi_n be passed along the way until to pi prime?
Depends on if you need it. So usually yes, yeah. So you just sort of like passing it along, some sense. So in SP1 at least they do this two-phase thing. In the first phase, they actually commit to the traces in the first phase and then only then prove them in the second phase. So they actually like generate traces twice.
Sorry, I don't get the last one.
So they generate and they have two phases of trace generation and the proving phase. The first phase, they generate traces to be able to commit to them, and then in the second phase, they take, and that's mostly for fiat engineering. So they commit to all of them at once and then take the hash of those the transcript basically when you're committing to all of them. Because the thing is, for the memory argument, you need memory consistency across all the different shards that they call it shards, but shards is basically like this from pi1 to pi_n shard groups. So they do have to split things up into two phases. So we can go more into it later on, if you're curious. But yeah, I think this is pretty much what I wanted to talk about for proofs. And I'll quickly wrap up, I guess. I think when I talk about things like this, I guess, like this system, it seems like most teams are using this sort of style of building zkVMs. So, like, what I was talking about mainly, like, you can see like SP1 is doing something similar, and RISC0. That's not the right sign, but so like argument is using spings, right? They created spings, which is like a fork of SP1. Jolt. So Jolt is also RISC-V, right? But they changed the instruction set a bit. Nexus as well, actually. So Nexus. There's also like a Nita, right? And Minen and Cairo. I think I'll put them somewhere. It's a bit. Yeah. So you can think of them as like using like RISC-V here. Let's see. Sort of RISC-V, like here, maybe here, right? And then they're they're using also a reduced instruction set actually. They're doing using sort of like a RISC architecture. And then they're sort of using these teams are using their own ISA. Right? They have like the Minen instruction set and then like the kind of instructions.
Okay.
And these teams are sort of using Starks, right? And then if I'm not wrong, Jodes is I didn't look too much into them, but I think they're using Starks generally.
So.
Look about this.
Yeah. Sorry?
Based on some lookup algorithm.
Yeah.
Awesome.
Yeah. So there's like two ways to categorize them, I guess. One, either you would think of them as like in terms of instruction sets, in the sense they're all using like the RISC style instruction sets here, and these teams are sort of doing their own instruction sets. The second way to think about them is the Starks versus Snarks, which I think is not too useful. But yeah, that's another discussion, I guess. But all these teams are using Starks, and then these teams are using Snarks. But yeah.
Is WebAssembly also an ISA?
Sorry?
Is WebAssembly also an ISA? Yeah.
I guess you can think of them as an ISA.
It's
But not quite, right? But I haven't. I didn't. Maybe you're talking about the zkVMs.
Yeah.
Yeah, I don't know too much about them, so. But yeah, that's what I wanted to share. Happy to take questions, I guess. Oh, sorry. Happy to take questions or.